Hey there, guys and gals. We are in. Sorry, I had to check look at what I was doing. What video am I even making? We are in chapter 2, lesson 1 of Algebra 2. We're going to take a look at this. We're going to look at relations and functions. This is going to be some review and some taking some Algebra 1 concepts and kind of making them more specific. We're going to add some vocabulary. We're going to do a handful of examples, and then we're going to be done. In this video, we're talking about relations and functions. We're going to kind of, for the most part, assume that you guys know from Algebra 1 what a function is. I'm going to kind of I'm going to kind of assume that. I'll say some things and we'll review some things. So we're going to assume that you know that a function is a type of relation where for every input, every piece of the domain, there's only one output. That's a function, right? So this is a picture of a function. It happens to be a one-to-one function. I'll explain that in a second. But I want to note, just for the sake of kind of just dusting off cobwebs a little bit, basically, if you have something like this, where you have two members of the domain here pointing to two different outputs or parts of the range, then that's not a function anymore. It's still a relation, but it's not a function. So I wanted to remind you of that fact before we go any further. Now, we're going to get some vocabulary here at the beginning of some specific types of functions. This first picture is illustrating, as it says here, a one-to-one function. And so what a one-to-one function is it's a function where every single member of the domain is pointing to an output, right? So something that would not be a one-to-one function would be like if we took this part out, right? If we take that part out where this piece of the domain doesn't have an output, that's not a one-to-one function anymore. Okay, so this right here is a one-to-one function when we have every single piece pointing to an output, right? Now, the next type of function we're going to talk about is an on-to function. So an on-to function is one where every single... Sorry, I had a brain scariness and I thought I was about to say a lie, but I wasn't about to say the lie. I should have just kept going. Why are you not? Oh, there you go. I should have just kept going and saying the words, but I don't know. Sometimes that happens. Curse of an ADHD brain, I suppose. Sorry, you get a distracting thought. Anyway, so an on-to function is one where every member of the range is mapped, has something coming to it. Now, you notice this particular on-to function, it has where the 2 has an output or is mapped to a y, and the 3 is also mapped to a y. Now, it's very important, this again, kind of dusting off those cobwebs, it's important to note that this is still a function. You can have two different members of the domain pointing to the same output. This could be something, if we're putting it into kind of mathy terms, this could be something like a parabola where we have two different things that are have the same output or the same y value, right? So it could be something like that. We'll get more and more specific about those kind of things later when we get into parabolas and all that kind of stuff. But so an on-to function is all of the range. So if we compare that to this one, I didn't mean to do that. This one would not be on-to, right? Because this 3 here doesn't have anything mapped from the domain to it. So this particular one right here is not on-to. This one is on-to. Now we can have, like this third example, we can have a function that is both one-to-one. So every member of the domain is mapped to a member of the range. So it's both one-to-one and on-to. They all have something that is mapped to it, right? So those are some different types of functions. Let's flip to the next thing. So another thing that a function can be is a function can be either discrete or continuous. Now, it's worth noting that some of the definitions here in Algebra 2, there are more formal versions of these. The higher you get in math, we get more and more formal. So sometimes we give kind of like pieces of a definition, that statement isn't going to matter to most people that watch this video. But I'm going to throw that out there just because. So the difference, for the sake of our class, is between a discrete and a continuous function. Continuous is pretty easy, right? It's something that continues. So something like this would be continuous, or even something like that. Those are both examples of continuous functions. They don't have any gaps. They don't have any breaks. They don't have any hard corners. They don't have any of those kind of things. Now, something like this would be a discrete function. It has discrete individual pieces, right? So those, now, this is more kind of advanced, but I'm going to throw this out there just to kind of put this in for later in like a pre-calculus class or even a college algebra class. You can have some functions, you'll see later, where it has portions that are discrete and portions that are continuous, right? And so that's more future knowledge, but that you can have a function that has both of these two things in one. All right, next thing. So the next thing is a vertical line test. Now, this one is one that you probably saw in Algebra 1, but we're going to remind you of it here. So vertical line test, I was saying earlier that in order for a relation to be a function, it has to have, for every input, for every piece of the domain, it can only have one output, right? So vertical line test is a way to check to see whether something is a function by using a test. And so it looks like this. Let's draw a couple of relations. I'm going to draw, let's do one in this bright green color. So let's do this guy. That looks great. And then we'll do another one on this same graph. We'll use a different color. How about this pretty little purple color? And let's do this relation. Okay. Now that we got those puzzle pieces on there, let's grab me a pink color to use the vertical line test. So the vertical line test is a way to check and see whether this purple graph or this green graph are functions or not. Okay. And so the way you do it, and usually when I'm teaching like in person or something, I tell the student to kind of take their pencil and run it over the graph. And if their pencil touches the graph ever in more than one place, it's not a function. Let me kind of put some lines on here to show you. So like if I was running, let me make this brush a little smaller. Is that good enough? Yeah, that's, well, maybe even a little smaller than that. That's great. That's kind of what I want right there. Okay, so if I'm running my pencil, never mind the little diagonal thing, that was a mistake. If I'm running my pencil across the graph, you can see that as I'm running across this green line, this never is touching. Each one of these is kind of representing the pencil over time, right? It's never, like this guy's never, it only touches it once right there. Once right there. Once right there. And as I'm going, it never hits this green graph more than once. So this green graph is, well, I better make my thing a little bit bigger so my writing doesn't go all spooky. Okay, it is a function because it passes the vertical line test. Now, this purple one, it's really easy to see with this little pink stuttered line right here. This one, as I'm bringing my pencil across, it touches the purple graph here and here at the same time, right? And so it hits it twice, and it does it pretty much throughout its entire place. The only place it doesn't is right here at the vertex of this sideways parabola. And so this one is not a function. Not a function, right? Because it fails the vertical line test. So that's, again, another kind of dropping some stuff off of or dropping some cobwebs off and dusting off some things from our rememberies. Now, let's look at an example of some stuff with a function. Let's do this guy. So we're going to do this example right here. We are going to graph y equals 2/3 x plus 2. Now, this is, again, something that I'm going to assume that you know how to do. If you don't know how to graph a line, then you probably want to go check out my videos on graphing a line or somebody else's, and make sure you know how to graph a line. Because if you don't know how to do at least that in our Algebra 2 class, you definitely need to kind of go back and review it. But anyways, we're going to assume you know how to do it. We're going to practice it here. Graph that line and determine the domain and range. Then we're going to determine whether the equation is a function. Is it 1-to-1? Is it on-to? Is it both? Is it neither? We're going to also state whether it is discrete or continuous. So let's start out by graphing the thing. So to graph this, it's already in slope-intercept form, really easy peasy. Just as by way of really quick review, slope-intercept form is y equals mx plus b. The b is the y-intercept, so our y-intercept here is 2. So we're going to go up to 1, 2, and we're going to put a dot, right? And then our slope is 2/3. Slope, the m part, is rise over run, right? You remember that? Easy peasy, lemon squeezy, right? So we're going to go up 2, 1, 2. We know to go up because it's positive. Up 1, 2, and then over 1, 2, 3. All right, if I was doing this on paper, I'd probably put at least 3 dots on there. That way I have something to line up my ruler with. So up 1, 2, and then over 1, 2, 3 again. All right, then we're going to connect the dots. I'm going to do the best I can to do that with a more or less straight line. I don't really have a ruler on here. That's something close to that, right? So that's what she looks like. There it is. It's beautiful. Okay, so let's do the domain and the range. So what are domain and range? We're going to remember what that is. Dust off those cobwebs. Domain is a list of all possible x's, all possible inputs into the function, right? So the domain of this. So what you want to, and with linear functions like this one is, it's the domain and range are easy, right? If you remember domain and range very well, you can probably already tell me what they are. But later, as stuff gets more complicated, then the domain and range kind of changes, and it's easier. And I'm kind of putting this seed in for later in our class, that it's kind of easier to think about the domain and the range almost in reverse. And so it's easier. You want to kind of think, is there anything that we cannot put in for x? So in this case, is there any numbers that if I put it into x, something bad happens? And by something bad, let me kind of give an example of something that could be a problem. Like if I have, and we may see something like this later, spoiler alert, if I have something where I have 1 over x, if I was to put a 0 in here, I'd have a problem, right? I can't divide by 0. So that's an example of what I'm talking about. We'll see more and more of that later as we go. But in this case, there's nothing that I cannot put in for x. I can put any real number. So the domain of this function is, as you might have figured out, might already know, the domain is all real numbers. Okay. Now, later on, and in other classes and other things, that there are more formal ways to write this, and we'll talk about that in pre-cal. And I can't remember. We may hit that in this class later. I don't know. But there are more formal ways to write that. But for now, this is great. So the domain is all real numbers. Now, is there anything that y is not going to be able to be? Well, no, not at all. So the range is the same. The range in this case is also all real numbers, because any real number we can put in, or in this case get out, because it's the output, right? So there's the domain, easy peasy. So is it a function? Well, it passes the vertical line test. It does, right? If we're taking our imaginary pencil and we're going across here, sorry, I need to take my finger off the shift key. That's where I'm getting these weirdnesses. But as I pass the vertical line through, it never touches it more than once. So it passes. So it is a function. Great. Okay. So is it one-to-one? Is it onto, both, or neither? Well, for this one, it is actually both. It is both onto and one-to-one. I'm going to write it and then I'll explain it. Both one-to-one and onto. Okay, so it's for every x on here, every input. So let's say right here, for every x, I have an output. For every x, I have a y. For every single one, I have x. For every single x, there's also y. It's a whole set of ordered pairs, right? If I was to somehow be able to list out the infinite domain that is here, every single x would have a y going with it. And so if every single x has a y going with it, then it's both onto and one-to-one. And let's see, discrete or continuous, there's no holes, there's no weird sharp points, none of those things. It is continuous. Easy peasy, right? So we got a couple more vocabularies and one more example, and then we are through with this lesson. So these are the last bits of vocabulary we're going to talk about, and that is the independent and the dependent quantity. So the independent quantity is all of the x's, which are all the inputs, right? And it's the variable that changes, that if it changes on its own. Now, I like to, especially at this point in Algebra 2, you may be in physics or have taken physics or are going to take physics or chemistry or some other, math-heavy sciences. You may have been in some of those already. And so that's these real-life situations is where we kind of talk about the independent and the dependent. And you'll be asked in your homework or in a science class, what is our independent variable, our independent quantity, and what is our dependent quantity? And the easiest way to think about that in a word problem is just use the root of the word. One of the things, the variables are whatever's changing, right? You might have an experiment where there is time that's changing, time is marching forward, and you're measuring time, and you might have temperature, right? And so time and temperature might be variables, right? And so the way to figure out which one's independent, which one's dependent, is figure out which one depends on the other. Also, throwing this out there, I chose time as my kind of ethereal example on purpose. If you ever have time as a variable in an experiment or a word problem, it is pretty much always the independent variable because we can't control time. We can't change time, right? So that's what's going on. So when we go with independent and dependent, the independent variable is the x's, which means the dependent variable is the y's. The independent variable is the inputs into the function, which means the dependent is the outputs, which starts with an O, not an A. Outputs. Right? Okay, let's do one more example, and then we're going to call this lesson quits. Okay, so function notation that's not a function. A function is concept, a function is an idea, but function notation is this f of x thing. Now, this is probably review for you, probably, right? But let's remember how to use it. So if we have the function and we say this f of x, and it's really important, I hope you know this from your Algebra 1, but if not, take the time to remind you here that this does not mean times. This is not equal to f times x. That is not what that means. It is f is a function of x. And what this tells us, going back to kind of our last concept that we were just talking about, it basically tells us what the independent and dependent variables are something, I don't know, grammar. You got it, right? It's what this notation is telling us is that x, whatever x is. It could be x, it could be t, it could be chicken. I don't know. Whatever it is. That is the independent variable. And this whole big thing together, that's the dependent variable. And that's what this notation does. And that's why we kind of graduate into function notation instead of just regular like y notation. Because as what this is this is basically y. It just tells us a little bit more, and it has a little bit more functionality. So it's more useful and more descriptive. And so that's why we graduate into function notation. So on a problem like this, where it gives you a function in function notation and it wants you to find these things, it's just a substitution problem, right? And so to find f of 6, all we do is we rewrite this mess with parentheses everywhere there's a variable. So we're going to write it as 2 times, and then squared minus 8. And then we're going to take and plug in this where the x was. So we're going to take and we're going to put a 6 right there. And then you just simplify it on down, right? So 6 squared is 36. And then bring down our minus 8. 2 times 36 is 72. And then bring down minus 8. 72 minus 8 is what? 64? Does that sound right? And 64. Looks right to me. If it's not, let me know in the comments. Or in class or something. So f of 6 is 64. Let's do this one real quick. So this one's got a letter in it still. So we're going to end up with some weirdness. It's actually, you know, it's funny because you would think this would be easier because there's no letters. But honestly, this one's going to be easier because the math is going to be simpler. It's going to end up with an uglier answer, but it's going to be easier for me to do in my head instead of taking all of our time to bring up my calculator. So we're going to start out the same way. We're going to rewrite this with parentheses where the variable is. And then we're going to plug this whole thing in for the variable. So we're going to put a 2y right there. So now what are we going to do? Well, we're going to do 2y squared. So what's 2 squared? 4. So we're going to bring down 2 times 4. What's y squared? Y squared. Wow. Easy peasy. And then bring down minus 2. So we've got these guys multiplied. 2 times 4 is 8. So 8y squared minus 2. Those are not like terms. That's as simple as it gets. F of 2y is 8y squared minus 2. And that is the last bit for this video. Wow, we're about 20-ish minutes. I thought this video was going to take longer than that. I'm glad it didn't for all of our sakes. Thank you guys for joining us. If you're one of my students, I'll see you in class, do your homework, all those things. If you're not one of my students, hope this was helpful. Let us know how we can help you with math or science or homeschooling in general. We'll see you later. Bye-bye.